All right, so we've been looking at this idea of summing up rectangles underneath a curve in order to get the area, or the exact area. And so when we do the rectangles, we refer to those as Riemann sums. Well, after we get to those infinite rectangles, we then create a new notation for calculus called integrals. So I wanted to show you a quick little animation of what it looks like when we start talking about these rectangles. Okay, you've seen this a little bit from just our drawings and kind of how they play out, but obviously our drawings are not as good as an animation would be. So let's see if that plays. Okay, so what's happening here is over here we have a left-hand rule. We're using left-hand heights. In the middle we have a right-hand rule using right-hand heights. And then over here we have a midpoint rule using midpoint heights. The actual area we are looking for is 2, this dashed line. And what you'll see is that our underestimate, our overestimate, our midpoint estimate start to collide with one another as we start to increase the number of rectangles. Well, as the rectangles get really big, or your partition gets infinitely small, we end up getting closer and closer to our exact area with very little error. So hopefully that paused. Good. So if we look here, this is still just a little bit too low. When we get zoomed in, we're just missing a little bit of area. This one is a little bit too high, okay? And this one, it's like kind of hard to tell because you got a little over, but a little under, a little over, a little under. So our midpoint rule is our better approximation, all right? Our right-hand rule in this case, because this function was increasing, right-hand rule is overestimating. Because this function is increasing, left-hand rule is underestimating. But this is kind of what you should picture, is that, again, your rectangles, as you increase the number of rectangles, watch what happens to the width of them, the change in x, or the partition and the width. As the number of rectangles gets bigger and bigger, the width gets smaller and smaller because you're trying to fit in more and more rectangles. Okay, so delta x is infinitesimally small as we start to increase that number of rectangles. All right, so that's enough for YouTube. Close that out. All right, so let's look at your notes then. Riemann sums and integral notation. So we saw the exact area, remember no longer estimating, the exact area under a curve, bounded by the x-axis and 2 other values, a and b, which was our partition. Okay, that's our full interval that we're looking at, could be found using the following limit with infinite rectangles. So the width was b minus a over n. The function, if we stick with the right-hand rule, which we were, is a plus b minus a over n times I. And then we're going to sum that all up. I equals 1 to n. F of a plus b minus a over n I. All times our width, which was b minus a over n. And then we said in our ideal world, we wanted to have our number of rectangles get infinitely big. And once we get those infinite rectangles, we no longer are estimating, we are actually finding the area trapped under that curve. So the name for finding the exact area under the curve using this process as n goes to infinity is called a definite integral. Okay, a definite integral is finding the exact area under a curve. Okay, we say under because generally we trap to the x-axis. We'll see some different scenarios over the coming weeks, but what we want to make sure comes out of a definite integral is a number that represents the area on a coordinate plane. All right, so here's our integral notation. This limit, I'm going to use yellow for this, and you'll see why in just a second. This limit as n goes to infinity of the sigma all gets nicely replaced with this fancy integral sign, which is really just an elongated letter S. S for sum, because you are summing up those infinite rectangles, okay? Our f of x, right, is right here. F of x, that was our function. We're used to that. Our b minus a over n, that becomes our change in x, right? How big is each little partition? So that becomes dx representing delta x or the change in x, the width of each rectangle. So the last things here I have to deal with are this a and b. Well, a is our starting value, and b is going to be our end value. So what this integral is saying is sum up the area from a to b of f of x dx. So f of x represents the height, dx then represents the infinitely small width of each rectangle. Because as the number of rectangles gets big, the size of each rectangle gets infinitely small. Note that the dx we have seen before. X here also represents then your independent axis. So I'm taking areas where I'm drawing perpendicular to the x-axis. These are all x's, right? Delta x's. You can anticipate we'll have delta y and others coming up shortly. All right, so the purpose of this video is really just to do some translation from one to the other. Because right now, if you see this limit mess, you know how to set this all up. Use your summation formulas, take the limit as n goes to infinity, comparing the top heavy, bottom heavy, even heavy, all of that. So now what we want to do is we want to say, okay, if I'm given this, what is this actually finding? Because again, this notation tells us so much nicer to sum up the area, I have to keep switching on my colors, from A to B underneath the function f of x perpendicular to or with respect to those infinitely small rectangles along the x-axis. All right, so let's translate. This whole thing tells me I'm supposed to sum up an infinite number of rectangles. I'm going to use A and B in black. Hopefully that's okay. My A value is 3. My B value is kind of hidden inside of this 5. Well, what I know is that 5 is supposed to be equal to B minus A, which means B has to be equal to 8. My function, f of x, is just f of x. I don't know what the function is. It's still in general notation. And then my width, as n gets infinitely big, 5 divided by an infinite number is going to get infinitely small. So dx, okay? So what this means is that if you were to see this integral, it would mean do that. All right, let's try another one. So this limit as n goes to infinity says, hey, sum up an infinite number of rectangles from 2. Well, I know that 10 is equal to b minus a, so b is going to be equal to 12. This time, my function is no longer f of x. My function here is taking all of this stuff, squaring it, and adding 4. So my function is actually x squared plus 4. And then remember, this part again just always represents my width getting infinitely small. Okay. Again, if you were to see this, it means, hey, do this. Last one, I want you to pause the video and try on your own and then come back and see what you get. So go ahead and pause. Pause. Pause your video. All right, so hopefully you got the sum from 3, because of this a value right here, till 7, because 3 plus that 4 gets you to 7, or you could also say 4 is equal to b minus 3, so b is equal to 7. That's fine too. We have 12 times that whole input. So remember that input is like our big x value. So 12x plus 9, and then our 4 over n represents our infinitely small width, or our dx, change in x rectangle. All right, well, if we can go from summations to integrals, what we also want to be able to do is know how to go from an integral to a summation, because what's going to happen is I'm going to give you a problem like this and say, hey, find me the area between 5 and 9 under x squared minus 3 with respect to the x-axis. And you're going to look at me and you're going to say, Ms. Schwartz, That seems crazy. How am I supposed to do that? That's a curve. Exactly what the old mathematicians used to say. And then, that was a terrible, covered the 5, but that's okay. So the yellow part is what creates our limit as n goes to infinity, summing from I equals 1 to n. My width is going to be 9 minus 5 over n, so 4 over n. My function then, remember I want f of a, which is 5, plus 4 over n I. Well, this function says x squared minus 3. Well, here's f of x. So my x is going to be that 5 plus 4 over n I. Then I could do some algebra cleanup, go through, take the limit as n goes to infinity. Go ahead and try to go from this integral. Sum up the area between 11 and 13 under the function 4x plus 6 with respect to the x-axis. Pause your video and try that one. All right, so this one we get the limit as n goes to infinity, summing from I equals 1 to n. Our function would have been 4x plus 6, so it's 4a plus b minus a over ni plus 6, and then our width of each partition, or sorry, our width that's going to get us our infinite rectangles is 2 over n, because 13 minus 11. Hopefully that went okay for you guys. The next thing, there's a bunch of practice, and it says Riemann sums and integral group work to try. I would like for you to try this in your groups. I am going to make a video, though, about pages 18 and 19, but this was really today's lesson, okay? This is what you were supposed to learn, and then now it's supposed to be time to just practice. So go ahead and do that if you would, please. Yeah, and we'll reconvene when I see you.